We've all seen those spectacular animations of supernovas, a star's last glorious explosion, and for decades we thought of them as the biggest fireworks show in the cosmos. But they're not. The real show, the kind of event so violent it forges gold, so powerful it shakes the fabric of the universe, happens when stars don't just die, it's what happens when they crash. So forget what you think you know about cosmic power. The most extreme, universe-altering events aren't about how stars end. It's about what happens when their dead cores collide. These are the smash-ups that have kicked off a new era in astronomy. One where we don't just see the cosmos anymore. Now we can actually hear it. To understand this cosmic demolition derby, you have to meet the contenders. Neutron stars. These aren't really stars anymore. They're the unbelievably dense corpses left behind after a massive star goes supernova. Think of them as the universe's ultimate zombies. Imagine crushing our sun, a star you could fit 1 million Earths into, down to the size of a city. That's a neutron star. A single teaspoon of it would weigh billions of tons, as much as Mount Everest. Its gravity is so intense, its escape velocity is more than half the speed of light. And they're born spinning, sometimes hundreds of times a second, whipping beams of energy through space like terrifying cosmic lighthouses. For a long time, these things were just fascinating theories. But we know now they're very real, and they rarely travel alone. In the vastness of space, many stars are born in pairs, locked in a gravitational dance for billions of years. So when two massive stars in a binary system both go supernova and leave behind neutron stars, the stage is set for a catastrophe. They become ticking time bombs, destined to give the universe one of its most spectacular shows. Picture it, two stellar corpses, each packing the mass of our sun into a city-sized ball, circling each other in a relentless death spiral. They might start thousands of kilometers apart, but their fate is sealed. Why? Because Albert Einstein told us so. His theory of general relativity predicted that these two incredibly massive objects, whipping around each other at insane speeds, are constantly churning the very fabric of space-time. They create ripples called gravitational waves. These waves aren't like light traveling through space, they are a stretching and squeezing of space itself. Think of two bowling balls spiraling on a trampoline. They make waves in the fabric, and those waves carry away energy. For our two neutron stars, losing that energy is a death sentence for their orbit. Slowly at first, then faster and faster, they draw closer together. For millions of years, they whisper their impending doom across the cosmos through these faint waves. But in the final moments, as they approach the speed of light, those whispers become a scream. The frequency and intensity ramp up into a final deafening chirp that observatories like LIGO and Virgo can actually hear. On August 17, 2017, we heard that sound for the first time, a chirp that had traveled 130 million years to reach us. It was the sound of two neutron stars dying, and it told us the main event was about to begin. In the last fraction of a second, two atomic nuclei the size of cities, each weighing more than our sun, slam into each other. The violence of this moment is almost beyond our ability to comprehend. This isn't just a car crash, it's a fundamental reordering of matter and energy at the most extreme level. The impact unleashes a wave of energy that makes a supernova look like a flicker. First, a brilliant flash of high-energy light called a short gamma-ray burst erupts. For decades, astronomers wondered where these powerful seconds-long bursts came from. Now we know, many are the birth cries of a new cosmic monster. At the same time, the collision shreds the neutron stars, flinging vast streams of hyper-dense neutron-rich material into space at a huge fraction of the speed of light. This cloud of debris, glowing from the raw heat of the crash and the radioactive decay of new elements, creates a spectacular and unique explosion called a kilonova. First seen in detail after that 2017 event, a kilonova is 1,000 times brighter than a regular nova. It's a beautiful, fleeting afterglow, a forge of the gods, briefly lighting up the cosmos. The two stars that began this dance are, for all intents and purposes, gone, their matter and energy swept up in this cataclysmic transformation. So, after the gravitational scream and the flash of light fade away, what's actually left? The answer comes in 3 parts, and it's far more incredible than just a pile of stellar wreckage. First, the remnant. The combined mass of the two neutron stars collapses into a single object. For a split second, it might form a spinning hypermassive neutron star. But in most cases, this object is just too heavy to fight its own gravity. It blows past the cosmic weight limit known as the Tolman-Oppenheimer-Volkoff limit. Gravity wins. The remnant collapses catastrophically, creating a brand new spinning black hole. The stars are now a singularity, a point of infinite density where nothing, not even light, can escape. Second, there's the invisible remnant, the gravitational waves themselves. These ripples are the echo of the collision, and they're a direct confirmation of Einstein's century-old theory. The GW 170817 event was so revolutionary because we didn't just see the kilonova's light, we heard the collision that created it. The gravitational wave signal arrived just 2 seconds before the gamma ray burst, the first time we ever observed an event with both light and space-time ripples. It's like seeing a distant flash of lightning and hearing the thunder almost at the same time. These waves have given humanity a new sense, a new way to map the universe's most violent and hidden events. And finally, you have the collision's most tangible legacy, cosmic alchemy. That cloud of ejected material from the kilonova is a chemistry lab from hell. Inside this superheated, neutron-rich furnace, a process called the rapid neutron capture process, or R process, goes into overdrive. Atomic nuclei are furiously blasted with neutrons, growing heavier and heavier in mere seconds. This is where the universe forges the bottom half of the periodic table. The GW 170817 event is estimated to have created up to 16,000 times the mass of the Earth in new heavy elements. This includes about 10 Earth masses of pure gold and platinum, all hurled out into space. It's events like this that are rewriting our understanding of the universe. We've moved from just looking at the sky to listening to it. If you find these cosmic mysteries as mind-blowing as I do, make sure to subscribe and hit that notification bell. We are constantly exploring the new frontiers of astronomy, and you won't want to miss what we find next. So, what's really left after two stars collide? It's not a smoldering ruin, and it's not just a black hole. What's left is a permanent echo, a story written into the fabric of the universe itself. It leaves behind a signature in space-time, a gravitational wave that carries the tale of the star's final, frantic moments across millions of light-years. It leaves behind a ghost in the form of a black hole, an object that will warp space and time around it forever. And most poetically, it leaves behind the seeds for future worlds. The gold in your jewelry, the platinum in your phone, the tellurium recently spotted by the James Webb Space Telescope in another kilonova. These precious heavy elements weren't born in ordinary stars. They were forged in these brief, cataclysmic collisions and scattered across the galaxy. Billions of years ago, a smash-up just like this may have seeded the cloud of gas and dust that eventually formed our solar system, our planet, and even us. So the next time you look at the night sky, remember that the most powerful events aren't always the bright ones. They are the silent, universe-shaking collisions that we're only now learning how to hear. They don't just destroy stars, they reshape the cosmos and create the very treasures we find right here on Earth. Subscribe for more cosmic collisions.